Sometimes when we're testing for disease, the manufacturer gives us information about their test, how well it works. Now, the information that they give us, the numbers that they choose, don't translate immediately into what our opinion would be about whether we have a disease, given that we tested positive or negative. But using Bayes' theorem, we can transform their information into the opinions that we would like to state. So let's let T be the event that the test is positive. That is, that it says the person has a disease. And let's let D be the event that a person actually has the disease. So sometimes the available information is the false positive probability. That is the probability that the test is positive given that a person does not have the disease. And also available is probably the false negative probability. The probability that the test says a person does not have the disease when they actually do. So people and organizations are more interested in the probability that somebody has the disease given that they tested positive, and the probability that the person has a disease given that they tested negative. And maybe the probability of not having the disease given that the test is positive, which is just 1 minus the probability of having the disease given the test is positive. Or the probability of not having the disease given that it's negative, which is 1 minus the probability of having the disease given that the test is negative. Now, by Bayes' formula, we have, let's do the probability of having the disease given that the test is negative. That's the probability of having the disease and having the test be negative over the probability that the test is negative, which is the probability of having the disease times the probability of having a negative test given the disease over the same thing, probability of having the disease given times the probability of negative test given the disease, plus the probability of not having the disease times the probability of a negative test given not having the disease. Similarly, if we want the probability of having the disease given that the test is positive, we'll just copy this formula with a T everywhere there's a not T. So the probability of having the disease given the positive test is probability of having the disease times probability of positive test given having the disease over probability of disease, probability of positive test given the disease, plus probability of not having the disease times probability of positive test given not having the disease. Alright, now before we do any computations, I want to give you a little bit of a warning. Both of these formulas involve P of D and P of not D. P of D and P of not D. So they both are very sensitive to the probability that somebody has the disease, our opinion about that before the test is given. So both formulas involve and in fact are very sensitive to probability of D and probability of not D. So let's look at extreme cases. So let's say we give the test only to people who have the disease. So we have a population of people who are known to have the disease, and we're just looking to see how the tests work. So probability of D equals 1, probability of not D equals 0. Then both formulas are, probability is 1. So we've got 1 times something over 1 times something plus 0 times something plus 0. So these are, it's expression over the same expression. So that's exactly 1. Same thing for here. Probability of D is 1. Then we keep these two terms, and that term goes away, becomes 0. So we've just got this expression over itself, so it's 1. Alright, and then in the other extreme, what if we give these tests to people who don't have the disease? Then the probability of having the disease is 0, and the probability of not having the disease is 1. And then both expressions are probability of D is that's supposed to be a 0. 0 times something over 0 times something. Plus 1 times something. 1 times something else, but it doesn't matter. I'll write a triangle, something else. 0 is in the numerator, so this is definitely going to be 0 no matter what star and triangle are. And down here, same thing. If probability of D is 0, we've got 0 over 0 plus something, which is going to be 0. So, in my opinion, this computation that we're doing, the probability of having a disease given that the test was negative, or the probability of having the disease given that the test is positive, is more interesting if our opinion before the test is close to 0.5. Let's say we're testing people who have all been exposed to somebody who has COVID or who have symptoms. So the exposure to somebody could have led into transmission of the disease, or it could have not happened. And then the symptoms could be the disease, or they could be common cold or some other cause. So these computations or most interesting when P of D and P of not D are close to 0.5. Because then we're saying something about how the test works, really, and not so much about the population that's being tested. So the computations say more about the test and less about the population being tested. So let's do some examples with numbers I got off the internet. And I'm not a medical doctor, so I don't know how accurate these numbers are, or even if I'm interpreting the numbers correctly that I got off the internet. But it looks like the rapid antigen test for COVID has, let's see, so the false positive probability of the test being positive given that the person does not have the disease is 0.014. And the false negative probability that the person tests negative even though they do have the disease is 0.154. So suppose people get tested so these people, half of whom have COVID, half of whom don't. Suppose these people get tested. So then we have the probability of someone having the disease given a positive test is probability of having the disease is 1/2 given the population that we're testing. Probability of testing positive given the disease is 1 minus the probability of testing negative given the disease. So 1 minus 0.154. Over 1/2, 1 minus 0.154, plus the probability of not having the disease is also 1/2. Probability of testing positive given that you're negative, 0.014. So I get that this is 0.846 over 0.860, approximately 0.984. So the probability of actually having the disease, given that the test is positive, is very high. All right, now let's look at the probability of having the disease, given that the test is negative. All right, so I'll erase these numbers. Actually, I'll put the 0.984 here. So now the probability of having the disease, given that the test is negative, is so probability of having the disease 1/2 times probability of having a negative test given the disease 0.154 over same thing 1/2 times 0.154 plus the probability of not having the disease 1/2 times the probability of testing negative given not having the disease. So that's 1 minus 0.014, because the probability of testing negative given not having the disease and the probability of testing positive given not having the disease have to add up to 1. So 1 minus 0.014. So I get that's 0.154 multiplying top and bottom by 2 to get rid of the 1/2 divided by 1.140, which is approximately equal to 0.135. So if these numbers I got on the internet are anywhere near accurate, it looks like even if you have a negative test, there's still sort of a significant probability that you have the disease, given this rapid antigen test, which is the one that a lot of organizations are saying they don't accept as proof that you don't have the disease. There's a 13.5% chance that you really do have the disease, even if the test is negative. So this is the rapid antigen test. Then somewhere else on the internet, I got some numbers that I'm maybe even less sure of. So the PCR test, the one that takes 2 days, has a false positive rate of 0.067. And a false negative rate of 0.013. Okay, same experiment. Say we've got a group of people, half of whom actually have COVID, half of whom don't. They've had some exposure to people with COVID, they have symptoms. Then let's see what the probability of having the disease given a positive test is. Maybe I'll save the numbers here. So for the rapid test, we had probability of having the disease given a positive test is 0.984. Probability of having the disease given a negative test is 0.135. Okay, so the probability of having the disease given that the test is positive is probability of having the disease, probability of testing positive given the disease. So that's 1 minus 0.013 divided by 1/2 1 minus 0.013 plus probability of not having the disease is also 1/2 times probability of testing positive given we don't have the disease. 0.067. So this is 0.987 over 1.02, 1.020, and that is approximately 0.968. So let me make another box here for the PCR test. So the probability of having disease given a positive test is 0.968. So it looks like this test is going to tell a couple more people that they have the disease who really don't. Alright, now let's look at the probability of having the disease given that the test is negative. So it's 1/2 probability of testing negative given having the disease, 0.013, over 1/2 times 0.013 plus probability of not having the disease times probability of testing negative given not having the disease. So that's 1 minus 0.067. So this is 0.013 over 0.946, which is approximately 0.014. So the probability of having the disease given that the test is negative is 0.014. So there's only about a 1% chance that you're ill with COVID if you get a negative result from the PCR test. So if these numbers that I got from the internet are accurate and I'm interpreting correctly what I read, we can see why an organization would trust you as not having the disease given that you got a negative test, more if your negative test was a negative PCR test than if your negative test was a rapid negative test. Because there's about 99, probability is about 99% that you're healthy if the test says you're healthy for a PCR, and there's only about an 87% test probability that you're healthy if the rapid test said that you're healthy. Now, having said that, I want to add a couple more warnings. From what I read on the internet, it looks like the numbers depend on age. And maybe other factors. Also, from what I read, it looks like if you're exposed to somebody with COVID and you don't have any symptoms and you get tested only 1 or 2 days afterward, the amount of virus in your system won't be enough to trigger the test. So if testing is done too soon after possible exposure, even after certain exposure, the virus level in the body may not be great enough to be detected. So it looks like it's better to wait at least 5 days if you don't have symptoms and you think you were exposed to someone with COVID, because if you wait less, the test might not tell you anything and you might have to go back and do the test again later. The end.